Hello and welcome back to the lecture of time series econometrics. So in this series of lectures, we have been discussing with the different mathematical properties of higher order AR and MA series. In the last lecture, we are actually going to talk about the variance of AR2 series. The reason we are talking about the variance part for AR2 series at the last is because we wanted to use some of the results that we have derived already, particularly the Yule-Walker equation. All right. Um, to begin with the derivation, we'll write the basically most favorite expression that we write for our AR2 equation is that yt phi 1 yt minus 1 phi 2 yt minus 2 and epsilon t. Now to get the variance term for the left hand side, you take variance for both the sides, right? So var yt is equal to, you take a variance for the whole term, right? T minus 1 phi 2 yt minus 2 plus epsilon t. Now, the second part of the equation, the right hand side of the equation could be basically what we do here is we basically use the variance rule for, say, a sum of three variables, right? So, var a plus b plus c, if we do, it is var a plus var b plus var c, right? Plus var c. And then we have the covariance terms, 2 cov AB, 2 cov BC, and 2 cov CA. So we use this formula here, 2 cov CA. So we'll use this formula here in expanding this right hand side, and we can write this equal to var phi 1 yt minus 1 plus var phi 2 yt minus 2 plus var epsilon t. And then we have our covariance terms, where we'll write 2 cov, we'll take two terms at a time, phi 1 yt minus 1, say, and phi 2 yt minus 2 plus 2 cov, let's write phi 1 yt minus 1 into epsilon t. And then we have another cov term, which is 2 cov phi 2 yt minus 2 epsilon t, right? Now, the equation might look pretty, scary a little bit, but it's nothing, it's actually pretty simple. And if we see this part, this term and this term, where we are multiplying phi 1 yt minus 1 with epsilon t and phi 2 yt minus 2 with epsilon t. So the covariance terms will vanish because these terms are independent, and when you take their expectation, they're actually going to be 0, right? So these two terms are going to be 0, so which will make our life easier. And if we now expand this equation further, so it will look like phi 1 square var yt minus 1 phi 2 square var yt minus 2, and var of epsilon t is nothing but my sigma e square. And then we have this term where we write 2 phi 1 phi 2, and then we have covariance yt minus 1 yt minus 2, right? Now we are going to use the notations that we have derived, that we have been using for variance and covariance. So what you write is, we'll write yt, let me use a different color because that's going to be an important equation here. So var yt is nothing but gamma 0. So basically we take gamma with lag 0, right? Var is basically, when I take the variance, that's lag is basically 0. And here when I write phi 1 square, now var yt minus 1, now you remember for the condition of stationarity, var yt and var yt minus 1 are basically same, so it will again be our gamma 0. And the second term, again, var yt minus 2, on the same principle, it will be gamma 0. It will be gamma 0. Now I have sigma e square, and the final term is basically 2 phi 1 phi 2. When I take the covariance, we see we are taking covariance between yt minus 1 yt minus 2, which basically means I'm taking a covariance. This is a covariance for lag 1, so I write gamma 1. So that's a very important equation, and I write it as my equation 1. Let me use another color. This is my equation 1. Okay. Now we have basically two unknown here. We have unknown gamma 0, we have unknown gamma 1, and we have one equation. So we really need another equation to solve gamma 0 and gamma 1. Basically, I need gamma 0. So to do that, now I'm going to introduce the results that we have obtained from Yule-Walker equation, right? And the Yule-Walker equation was gamma k, if you remember, equal to phi 1 gamma k minus 1 plus phi 2 gamma k minus 2, right? Now we substitute k equal to 1 for k equal to 1, okay? For k equal to 1, you will have gamma 1 is equal to phi 1 gamma 0 plus phi 2 gamma 1, right? Because we are assuming gamma 1 equal to gamma minus 1. We already explained this part. Now then again I have this equation with gamma 0 and gamma 1. So let me write down, this is my equation 2, right? So here again I have two unknown and one equation. So if I take both equation 1 and equation 2, so we have a system of equation where we have two unknown and two equations, right? So you should be able to solve it. So it's just a simple linear equation. I'm not going to solve it. So if you solve it, what you will get is gamma 0 is equal to 1 minus phi 2 by 1 plus phi 2, and then you have in the numerator sigma e square, and in the denominator you will have 1 minus phi 2 whole square minus phi 1 square, right? So that's basically the expression of variance for a AR2 process.